All right, so today we are looking at the conservation of energy. And the first thing that we're going to do, last week we saw work and how work relates to kinetic energy, but today we're going to look at an interesting form of work, which we call potential energy. Right? And this is basically, think of it as work which is independent of the path on which you are at, right? So it's basically work, if the work of a force the work of a force only depends on the differences in position. This work can be expressed using the energy term, what we call potential energy. All right. So what we're trying to say here is, let's take a look at an example, right? So if we have, a box that's traveling up some path, right? And you have a reference location, which let's say for our purpose here is the ground, right? And you start off, you're in some position, right? So let's say at this position, from that reference point, you're at height y1. And this is happening all under gravity, right? So this is the work done due to gravity. Right, and let's say that that is position 2. So that's going to be y2 like that. And then, between the paths, you're on this path. But as we'll see, that doesn't really matter, right? Because this energy is independent of path. And, to complete the picture, you have some small little change in position that might happen, right? So any position in the middle, your y, and then this, let's say this little change in position is dy, like that, right? And what we looked at last week was the work of force of gravity, right? And here the force due to gravity is due to the, whoa, really windy. For work due to force of gravity is the weight, right? And that's why we said that that was W. We'll see is that this work due to the force of gravity, we had found out, and we'd proven this, was actually independent of the path, right? All it was in this change of position. So it was independent of path, and it depends only on the initial and final values of y. And that's what's really interesting about potential energy, is because it only applies for these forces, which we're going to see are called conservative forces. But it really doesn't matter how you move from position 1 to position 2. All you're interested in is just the change in position. So it's independent of that path. All right. So if we take a look at the potential energy, which, by the way, kinetic energy, we said Ke, potential energy, we'll say PE, right? So the potential energy, we refer to it with the letter capital V. And here, it's because due to gravity, so we'll put a subscript G. That is the work done due to change in height Y, right? That is defined as the potential energy of this body with due to, so with respect to the force of gravity. Right, so if we take a look at the potential, the work done from getting from point 1 to point 2, you can say that that's basically equal to the potential energy of the body at position 1 minus the potential energy of the body at position 2, right? And this potential energy, you find that due to gravity, we know that that's just equal to, it's going to be mg y1 minus mg y2, like that, right? But what you have to remember is that when you're finding out these y1s and y2, you have to choose a reference line, right? And that reference line is called a datum. Ultimately, it does not really matter when you're looking at gravity where you choose the datum, right? So this choice of this datum can be completely arbitrary, right? Because it's a constant point. No matter where you choose it, that constant will just be deleted out of in this expression over here. All right, so this can be arbitrary, which just means that you can choose it wherever you want it to be. All right, so this is the potential energy due to gravity close to the surface of the Earth. If you want to look at stuff which is far away from the surface of the Earth, you start looking at space bodies, right? So you have the potential energy for space bodies, right? And that again, when you're talking about space, that again is due to gravity, right? And that's just equal to minus g times your big body mass times the small body mass over the distance that you have between them. All right, so here.
So potential energy is V. That's just the.
Yeah, that's the symbol that we use for potential energy, right? So for kinetic energy, we use T. For potential energy, we use V. For work, we use U. All right. Okay, so this describes everything that has to do with gravity, right? Next, we want to look at another interesting thing that comes in when you're looking at the springs, right? So when you're looking at springs, right, you have a spring. Let's say that over here, it's in its undeformed position. Undeformed, right? Or you have it getting deformed to a certain amount, and let's say that deformation in this position here is x1, right? Or you could deform it even further, right? Let's say that this deformation, elongation is x2, right? So the potential energy of a spring, typically in the textbook, you'll see that they use it with the subscript E, all that you can think of that as just being elastic, right? So that's what this E stands for. And this is equal to 1/2 times the spring constant times whatever elongation you have squared. All right. And this expression, you have to be careful when you use this. Here, the choice of the datum is not arbitrary. This is dependent upon, because you have a squared term here, you can't have it be arbitrary, right? So you have to measure the deflection from the undeformed position. So this expression is only valid if the deflection is measured from the undeformed position. Right. And you can express that again, how much work it takes from going from this position to this position, right? So that is the work done from going from position 1 to position 2 is just going to equal the potential energy at position 1 minus the potential energy at position 2. And that's just equal to half k x1 squared minus half k x2 squared, like that. All right, so this describes all of the potential energy that you guys would need for your problems. All right, next. And basically, these are all the tools that you need for essentially solving the problem. But, some more theoretical understanding or robustness is required, right? So potential energy only comes into play when you're looking at these forces called conservative forces, right? So let's see, what are these conservative forces? So you have conservative forces like that, right? So basically, whenever potential energy is coming into the picture, work is independent of path, right? So if the work of a force is independent. By the way, guys, moved here really quickly with this stuff, with the potential energy due to gravity and the energy in springs. Do you guys have any questions?
I had a quick question.
Yes.
The work from 1 to 2, is it negative since x2 is bigger than x1? And how do you explain that negative sign in a physical sense?
So the work done.
Yes.
So it's going to be yeah, the work done is from position 1 to position 2, right? So the work done, it's taking work to do this, right? So it's taking energy to do this. That's why the work done is negative. You're utilizing that energy into making that.
Okay, thank you.
Does that make sense? It's work being done, right? Don't get worried about the symbol over there. The important thing to note from here is what the potential energy is at that particular position, because that's what we're going to use when we use the conservation of energy. Yes, you're right. That does, and that's again when engineers and physics people start arguing with each other. How is it? What means what? But this, you can just see that it's the work being done to make this extension happen. So you can think of that as being negative. All right, so now if the work done of a force is independent of the path, so independent path, what we say is that the force is conservative. Right? So if we look at the work done, again, it's the same thing that we've been doing. You have the potential energy at position 1 minus the potential energy at position 2, right? If you have a conservative force along a closed path, right? So that's with this integral over here. You have this integral and you have this circle inside, which basically means that you're integrating over a closed path, which basically means that you end up at the same point at which you started, right? The work done ends up being equal to 0. And this is only true for conservative forces. So if you have a conservative force acting on your body and you end up at the same position, work done is 0, and the change in potential energy, therefore, is also equal to 0. And then, some people like to do things in vector form, right? So just to complete that definition, if you have infinitesimal work for 2 points, which are very close to each other, right? The change in energy is whatever you have the potential energy at position 1, and then you've moved on to this new position, right? But we're saying that they're infinitesimally close. So you'll have x plus dx, y plus dy, and z plus dz, like that, right? You can say that this is equal to a small change in potential energy at that particular position, right? And that, again, you'll see that it has this negative sign over here. For our purposes, what that means is that you have to do this work to make this this change happen, all right? And in terms of your forces, we know that you can write this out as being equal to fx times dx plus fy times dy. That's this du term, right? So this left-hand side over here, plus fz times dz. And if we look at this exact differential here, you can write it in terms of the partial differentials, right? We know this from calculus. So you have dou v over dou x times dx plus dou v over dou y times dy plus dou v over dou z times dz, like that, right? And if you take a look at these two expressions, you have dx, dy, dz, you can compare these terms, right? So if you look at that, what that means is that fx is equal to minus dou v over dou x. So basically what that says is that your force in the x direction is equal to the partial differential of the potential energy with respect to that direction, right? Dou x. Similarly for fy, you see that that's equal to minus dou v over dou y, and fz is equal to minus dou v over dou z, like that. Or what this means is, in a vector form, you can write out your force as being equal to just minus, you have dou v, partial v, partial x in the I hat direction, plus partial v, partial y in the j hat direction, plus partial v, partial z in the k hat direction, right? Or this, I hope, did you guys, I don't know if you saw this in calculus, but this is also called the gradient. So you can write minus grad of v, like that, all right? So that just has to do with the concepts of conservative forces. And this expression that you see over here, that your force is equal to the minus gradient of the potential energy, this expression is only true for conservative forces. So be careful about that. Not that we're going to use this for any intents and purposes, but for this derivation that you guys are seeing over here. All right, any questions? All right. Yes.
Do you happen to have an example for all these three cases? We don't have to solve the problems, just I want to tell them apart from just looking at a problem if I'm given this in an exam.
You're not going to be given this in the exam for dynamics, so don't worry about it. For the exam in dynamics, all you'll be asked to do is use the conservation of energy and the conservation of momentum, which we're just going to see right now. For us, this is just theory for you guys to understand how conservative forces work. We're not going to be applying this theory for our course at all. Does that answer your question? I guess it doesn't answer your question because I didn't give you an example, but yeah.
Yeah, that answers it. Thanks.
Okay, does anyone else have any questions? All right, so let's look at the conservation of energy, right? So when you have conservative forces that are working on the body, conservation of energy. Man, it feels like I'm teaching in Antarctica today. It's so windy. Can you guys hear that whistling?
Just barely
Yeah,
in the
we do.
background, yeah.
Yeah, very disturbing. Anyways, all right. So we've just seen that the work of a conservative force right, is just equal to the potential energy at position 1 minus the potential energy at position 2 when you're moving from position 1 to position 2. But what do we know from last week? What is this work done equal to as well? Right? What was this work done equal to? Yes.
The kinetic energy of 2 minus the kinetic energy of 1.
It was equal to, absolutely, thank you. It was equal to your change in kinetic energy. All right, so what does that mean? That means that your change in potential energy, but bear in mind it's 1 minus 2, is equal to your change in kinetic energy, which is 2 minus 1. Well, that flip things around, what you end up with is that the kinetic energy of position 1 plus the potential energy at position 1 is equal to the kinetic energy of position 2 plus the potential energy of position 2. Ultimately, what that means is that the sum of the kinetic and the potential energy when you have only conservative forces working on your body is constant, right? So ultimately what that means is that when you have only conservative forces acting on your body, your mechanical energy remains constant, right? So when only conservative forces are involved, the total mechanical energy remains constant. And what do we mean by mechanical energy? The mechanical energy is the sum of your kinetic and potential energy. All right. For most intents and purposes, the biggest force that we have to worry about that's going to be non-conservative is friction. And when you're using the principle of conservation of energy, you can still do it with friction, but you have to remember at that point, you're not really conserving energy anymore. You will have a work done term due to these frictional forces that gets lost to the surroundings. So if you account for that, you can still say that you're conserving energy and you're using that. And we're going to take a look at that in the first problem that we take a look at today. All right, and what's happening to the frictional this energy due to friction? You always lose it to the surroundings. Right, so basically what you have to do is when it's coming into the picture, make sure that you just take it out of your initial energy condition. So mechanical energy is dissipated by friction into heat, or we call thermal energy. And it's very interesting, you see this in this large scale dynamics that you see as well, but you also see this happening in material science when you're looking at strain energy and the changes of atom positions and things like that. Anyways, all right. So when you have motion under a conservative, now not only is, so when you have a conservative force, great, energy is conserved. When you have a conservative force that is also central, you will have, as we've seen before, you have conservation of angular momentum that takes place. So then you will have conservation of angular momentum and the conservation of energy that you're going to see. All right. So before we get into that, do you guys have any questions with this, with conservation of energy? Pretty straightforward, right? All right. So finally, we look at motion under a force that's not only conservative, but it's also central. Right? So what's the best example of this? Just looking at gravity, right? So let's say you have Earth and you have some satellite or something. It's on a parabolic axis, right? So let's just draw it with green. Start off with some position like that. You're in some path, let's say like that. You move on to another position over here, right? So, you know, you have your initial position, and then you have your general position, right? And then you've got the velocities, which are obviously tangential to the path, and then you can have the angle that the velocity makes with this vector, which is joining the center of both bodies, r naught, like that, right? Again, here you have random velocity there, blah, 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 and that makes some angle phi with the line that describes the joining of the position of the centers of these two particles over there, right? So in this case, which is this case which we've defined, which is an example of this motion under conservative central force, right over here, what you have is both the principle of conservation of angular momentum and you will have the conservation of energy. All right, and we remember from the principle of conservation of angular momentum that it's just in terms of all of these scalar quantities over here. In this initial position, you have r naught times m times the perpendicular velocity, right? So you have to take the component of that. So it's v naught times sine phi naught is equal to r mv sine phi, like that, right? So this is your first expression, and then your second expression is just that T naught plus V naught, right? So the total mechanical energy at this position is equal to the total mechanical energy at the second position, right? So it's T plus V, like that, right? And we know from what we've done so far that this expression here is just half m V naught squared. So this is the mass m, that's the mass m, like that, right? Minus, remember, potential energy for between two bodies, always negative. Don't listen to physicists. All right, it's minus gmm over r naught, like that. This is equal to 1/2 mv squared minus gmm over r. Now I know as engineers, we're terrible at using different letters for different things. Capital V, potential energy, small v, velocity. All right. So this is basically the same expression over here. So that's T naught, that's V naught, that's T, and that's V over there, right? This whole thing, in fact, is V. Cool. All right, guys, any questions here?
Can you zoom back in on that formula real quick?
Yeah. There you go.
So is it 2R0 on your drawing, like the one in?
Oh, yeah. Good catch. No, it's not. This is R.
Gotcha.
I have a question.
Yeah, what's up?